Okay, in this video I'm going to talk about how we can predict if a double displacement reaction is going to happen, or if it's going to happen in a meaningful way, and also if it isn't going to happen. So if we imagine taking two liquids that are containing ions. So imagine that we have our lithium iodide here. So essentially what that is a solution, and in that solution floating around are some lithium ions and some iodine ions. The solution as a whole is neutral, but the two things aren't associating with each other. That's what we mean by aqueous. That's why they spread out through the solution and we don't see them. And then we take a secondary beaker with our lead nitrate. What did I do? Lead 4? Lead 4. And a whole bunch of nitrate ions. I'm not going to draw enough, but there would be more than the PB because it's got to keep the whole solution neutral. Anyways, there should be, if I put 2 of those PBs, there should be 8 nitrates, but whatever. If I take those two and I mix them together, what I get is a big solution that's containing some lithium, some iodine, some nitrate, and some lead. That in itself doesn't constitute a chemical reaction. See, all these guys are floating around in solution. They're floating around in solution before. What's really changed about that? So what makes it into a chemical reaction is if there's a couple species in there that like each other enough that they'd like to come out of solution and form a solid or a precipitate. In this case, lead and iodine prefer to be in their crystal form than in the solution form. They prefer to form a crystal, and so they would crystallize and form a solid, and that's the precipitate, or that's the solid you'd see. If something like this exists, then we'd say that the double displacement reaction happened. If something like this doesn't exist, then in a sense there's no real meaningful reaction that's going on. We're taking two solutions with dissolved ions and mixing them together and getting a solution with lots of dissolved ions, but if those ions don't stick together, they haven't effectively changed in any way. So really, to predict if a double displacement reaction is going to happen, what we have to do is figure out, is there a precipitate or are there any things that are not soluble in water? How can we tell if something's soluble in water? Well, fortunately, we have this thing called the Solubility Table. The Solubility Table is a list of rules. They're in priority sequence, so the top rule is the most important, the second rule is the second most important. And then what these do is these tell us if things are soluble or insoluble. So for example, lithium iodide. Lithium is on the number 1 guideline, so that means that that's the most important ion in terms of determining the solubility of this product. Lithium is soluble, so I would say that that entire product is soluble. Lead nitrate. Lead is here, and nitrate's up here. So nitrate's on the higher guideline, and so nitrate is soluble, and that makes the entire compound soluble. Over here we have lithium and nitrate. Those are both going to be soluble, as I said, that they are both on the very soluble top line here. And then lead iodide. So lead and iodide both are not on the top list, so I go to guideline 2. Here I see my lead. It should be lead 2, and I've been using lead 4, but whatever. We'll just ignore that. In this case, lead is insoluble. That means that it's forming a solid in the solution. So before I get down to my guideline 3 here and I see iodine, I go in order. 1 is the most important, 2 is the second most important, 3. So since 2 is more than 3, lead makes this product insoluble. So that's how I use this. I start at the top, I look for stuff that I have, and I work my way down. Whenever I see what I have, I look to see if I'm soluble or insoluble, and then there's of course a couple minor exceptions. So let's just do a little practice here where we use the solubility table to see where we're at. Calcium chloride. Oops, let's try that again. Sorry. Calcium chloride. Calcium is here. Chloride is here. So since chloride is higher, he's more important. He's soluble, so I'm going to make that aqueous. Calcium sulfate. Calcium's here, sulfate's down here. Since the calcium is higher, he's more important, so this is insoluble. So I would say it would form a solid or a precipitate. Lithium carbonate. Lithium's up here. Carbonate's right here. Since lithium is in guideline 1 is more important than guideline 2, so lithium is soluble. Silver chloride. Here's my silver. Here's my chlorine. Silver is in guideline 2, which is more important than guideline 3, so I pay attention to my silver, and I say it's insoluble, or it forms a solid. Finally, iron hydroxide. Hydroxide is right here. Iron, what is it, iron 2 or 3? Doesn't matter. Iron 3 is right here. Hydroxide is clearly higher than iron, so this is the one that matters. It's insoluble, and so that forms a solid. So that's how we use this chart. We look through the chart for both ions. Whichever ion is higher in the chart is the one that matters more, and based on whether that ion tends to be soluble or insoluble, that's how we make the decision if the product or the compound is soluble or insoluble. Let's look at a few examples here. Sodium chloride mixing with ammonium nitrate. So I'm going to switch those up. Sodium nitrate and ammonium chloride. And now I'm going to check all of these in this chart to see if they're soluble or insoluble. Nitrate and sodium both make this soluble. Ammonia is right here, and chlorine, so this is very soluble as well. And so what does that mean? Well, I mix these things, but neither of the other products were any more insoluble than the initial things. So really what's going on here is this is an example of when all of these things are staying as ions in solution. And so effectively, there's no reaction here. Effectively, nobody's combining or forming something new. One more example, sodium chloride plus silver nitrate. Here my sodium would go with my nitrate, and my silver would go with my chloride. Now using sodium nitrate, I can see that that is very soluble. They're both right here and here, respectively, so they're both very soluble. Silver chloride, on the other hand, silver is higher on the list, and it's insoluble, so this is an insoluble product. What that means then is that when all these ions are hanging out in solution, if these two ions see each other, they would rather form a crystal than exist in solution, so these would form a precipitate. And this indicates a meaningful chemical reaction. And so this would take my clear liquid and my other clear liquid, mix them together, and something would all of a sudden start to appear in the solution. So that's how we use the solubility table to determine if something is soluble or insoluble, and then how we use whether or not something's insoluble or soluble to determine if a meaningful double displacement reaction has happened, or if really what we're dealing with is just a bunch of ions hanging out in solution.